Okay, continuing on with the ideas from the first video on this guide sheet. True or false statement question the first. According to the law of momentum conservation, if a collision occurs in an isolated system, so a system that's not affected by external forces, then any object involved in the collision will conserve its own momentum. Now, this is a false statement. It's a tempting statement, but it's false. And the key is its own momentum. In a collision between two objects, it is not the momentum of object A that stays the same, nor is it necessarily the momentum of object B that stays the same. They might, it's possible that they could end up with the same, but it's very unlikely. What's going to be the same is the momentum of the system. So if you take the momentum of object A and add it to the momentum of object B, and you look at that before the collision occurs, that will be equal to the momentum of object A plus the momentum of object B after the collision has occurred. Again, that collision might be an explosion, it might be a spring release, it could be any number of different things. We think of essentially three types of collisions: inelastic, where they stick together; elastic, where they bounce off; and superelastic, or explosions, where they fly apart. It's not that PA has to stay the same. It's not that the momentum of A is the same before and after. It's that the addition of both is the same before and after. This one might have gone from 2 to 1. Now, if this one had 1, the total over here would be 3. If this one dropped down to 1, that means this one would have had to take some extra. It would have transferred some momentum from A to B, and the total is what stays the same. So not the individual momenta of each individual object. Okay, now a big problem for people is the fact that we're looking at energy and momentum together at the same time. Energy is a scalar. With work, positive work means we're adding energy, negative work means we're taking energy away, but it has nothing to do with direction. Impulse and momentum are both vectors. That means you do have to be careful about the direction. So if you look at this situation here where an object is bouncing off a wall, so this is it's hitting into the wall at 5, and then it's coming out from the wall at 4. Compared to the same car, same mass, same type of car, which goes in at 5 and then sticks to the wall. We'd like to figure out which one would have the greater momentum change. Now, most people first looking at this would say, well, it went from 5 to 0. That's a delta V of 5 meters per second. Whereas this one went from 5 down to 4. That's only a change of 1 meter per second. No, 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 no. Okay. This one, if we take to the right positive and to the left negative, this velocity is positive 5 meters per second. This velocity is negative 4 meters per second. Now, delta V means you take your final velocity V and you subtract, it's a delta, it's a change, difference, the initial velocity U. So in our case A, delta V would actually be 5 positive minus a negative 4, which is actually a positive 9 meter per second difference. So while at first, with just casual glance, it looks like case A would be better for you, in fact, it's not. You're always better off absorbing the blow and sticking to something and losing that energy and that momentum rather than bouncing back off. Or in order to get you to turn around and move in the opposite direction, you have to get hit by a much larger force, have a much greater momentum change. Okay, so in which case does the speed with the greatest momentum change? It actually is case A. Greatest impulse, therefore, is in A, because the impulse and momentum are the same. The impulse encountered by the 800 kilogram car in case A would be 800 kilograms. Impulse, again, is force is equal to the change of momentum, which is 800 kilograms times the change of 9 meters per second. 800 times 9 is 7,200 Newton seconds. Letter E. So if you look at the change of momentum of B, it's 800 kilograms times 5 meters per second, which is only 4,000, not as much, only about half as much. Okay, so in a head-on collision, two cars stick together compared to when they rebound. Again, it's always better, in this case better meaning less delta P and therefore less change of less impulse if you stick. So if you look at cars, they are not designed to be battering rams that will or have elastic bands on the front which let them bounce back off. They actually have crumple zones which are designed to help get each car to stick together to reduce the overall amount of momentum transfer to the occupants. So car design is very different than you might think. It's not great to have a battering ram that's going to slice through, and you're better off in a collision having something that causes you to stick to each other. So the metal fenders are made to crumple and to give, just like if you're trying to catch a ball, you want to give with your hands, you don't want to just hold them stiff. Okay, 10 is just another reminder of this vector nature. Again, at first glance, it's like, well, case B doesn't seem to have much of a change. It went from 30 to 28. That's not much of a change. But you have to take into account the vector nature. It's not 30 minus 28. It's 30 positive plus or minus a negative 28. So it's a double negative, which becomes a positive, which means 58 meters per second. That's a pretty large change of velocity. This one, 10 to 5, well, it seems like it's only 5, but again, it's 10 minus a negative 5, which gives us a change of 15. Now, at first it's like, well, there's not a big difference in case B. It doesn't seem like much, but that's a very significant change in velocity and therefore a very significant change of momentum. So the greatest change of velocity, again, because velocity is a vector, direction does matter, is case B. You are subtracting a negative, which means you're actually going to add those two. In terms of greatest acceleration, in this case it looks like they're both the same object, so same size, type, and mass of object. So case A has a smaller change of velocity, therefore it would have a smaller acceleration. So therefore B would again have a greater change in velocity over that time period, and it would have a greater change of or greater acceleration value. So bigger delta V. Greatest delta P, change in momentum would be mass times the change in velocity. Again, the change in velocity is much larger in B. Okay, delta V again is much larger in section B, and momentum is change of momentum is mass times delta V. Again, they both are the same type of ball. They have the same type of momentum, same type of mass. Sorry. Then the greatest F delta T. F delta T is impulse. Again, impulse is the change is equal to the change of momentum. So if B has the greatest change of momentum, it must also have the largest impulse. So B has greatest delta P. Delta P is equal to the impulse, therefore change of momentum is equal to the impulse, therefore B must have the greatest impulse applied. Okay, so don't forget the vector nature of momentum. It's a tricky part because you're dealing with both a scalar, energy, and a vector, momentum. It can be easy to confuse the two and forget that they act in very different ways. All right, that's it for that part today. We'll get you number 3 next.